Good morning. The paper I've chosen for my individual reading assignment 2 is The Comprehensive Review of NASA's Human-Robot Interaction in Space. This paper is by Hambuchin, Kimberly, Jessica Marquez, and Terence Fong. This presentation is by Tanmayi, Inaparthy. So first we must ask the question, what is HRI? HRI refers to the dynamic collaboration between humans and robots where tasks are shared and coordinated. In the context of today's paper, we are going to look at HRI in the context of NASA's missions. Here, HRI is critical for optimizing operations in space exploration, enabling safety and effective interactions between astronauts and robots. And these interactions that we want to make effective will be in the exploration domain, the maintenance domain, resource utilization, and in habitat construction. So the objective of this presentation is to understand NASA's achievements in HRI, their current technologies, and their future goals. We will also highlight how NASA is meeting these challenges of deep space exploration while enhancing safety and efficiency and prioritizing mission success. So first, we look at the evolution of HRI in space missions. In 2011 to 2012, NASA experimented with smart spheres. These spheres, also known as the Synchronized Position Hold, Engage, and Reorient Experimental Satellites, are free-flying robots designed to assist with tasks aboard the International Space Station. So the objective here was to demonstrate ground control ability to interact with robots for tasks that are usually done by astronauts themselves. So these smart spheres were able to evaluate how robots can assist astronauts by handling routine tasks such as maintenance, video surveys, and even environmental monitoring. And these robots were semi-autonomous and could be controlled by astronauts or even the ground operators. They were small in shape and equipped with navigation and propulsion systems, which allowed them to float and move around the environment freely. Next, in 2013, NASA experimented with the K-10 series. The K-10 series is a planetary rover developed by NASA that had been tested for a variety of surface exploration tasks. Aboard the ISS, these astronauts could control these robots remotely on planetary surfaces such as on Mars and on the Moon. They had two levels of controls. One was through supervisory control and one was teleoperation. In supervisory control, we see that it's a high-level command where a human operator gives a broad high-level instruction. And the autonomy is sufficient enough where the robot can go through with the task without too much input. Whereas in teleoperation, we observe that it's a direct control, meaning the human directly controls the robot's movement in real time, for example, controlling its arm or some kind of wheel movement. So the outcome of the K-10 rover test series was that it proved that commands could be sequenced either from a remote surface through teleoperation or directly through ground controls. In the next evolution, we see from 2012 to 2018, NASA experimented with the Robonaut 2. So the Robonaut 2 was a humanoid robot developed by NASA designed to assist astronauts with various tasks aboard the International Space Station. It was developed as an effort to make sure that robots could get along with astronauts in space, which is why they wanted the robot to have a humanoid design, which means it has a head, a torso, 2 arms, 2 hands, which allowed it to perform tasks designated for humans, such as operating tools or flipping switches. It also had an assistive role, meaning it could help clean, maintain, and conduct repairs, allowing astronauts to focus on more important tasks. So the significance of this experiment was that it allowed and contributed to the ongoing efforts to integrate humanoid robots into human-robot teams. And then finally, we see the teleoperation experiments conducted by NASA as well through its popularly known teleoperation robot, the Canadarm, which was supported by the Space Station Remote Manipulator System, or also known as the SSRMS. So the SSRMS included a laptop, some hand controllers, 3 video monitors, and a display control panel, which meant there were many camera views that could help with checking procedures and many points of view so that if any errors were seen, they could be caught either by the 2 assistants on hand or by the ground control station. It's pivotal to note that the telerobotics operations on board were controlled by 2 people, one being the primary controller and the other being secondary. The primary controller was in charge of the translational and rotational hand control movements, whereas secondary was in charge of handling the camera views and making sure all the procedures were going in check. So this is important because someone should always be on the watch for any potential errors that could arise during operations that could actually be fatal to the space station itself. So now that we've seen what NASA has been working on, what are the challenges that NASA faces when they talk about HRI in a space environment? Well, space is harsh, meaning it has extreme conditions with high radiations, extreme temperatures, dust storms, and so on and so forth. So it's very difficult for robots to acclimate to that kind of environment if we don't send them prepared. At the same time, they also have to function in zero gravity environments. So, for example, when we see the space bees that were sent, they are programmed to work in those zero gravity environments. The other thing that it's a challenge that NASA faces is that there's a communication latency, meaning in order to communicate with a robot that's on Mars, they face almost 6 to 44 minutes delay. And in this time, the robot should be capable of handling its own tasks. So that level of autonomy, where even with latency, where there's no inputs from the human side, the robot should be able to make its own onboard decisions and be able to plan and execute some complicated tasks by itself. Then there's the aspect of technical risks and team dynamics. So when you're working with a robot, you have to be careful because they can't always be trusted. They're also a machine and machines can malfunction. And this kind of machine malfunctioning, especially in a high-risk environment like space, could lead to mission failure or even endanger astronauts. On top of that, we also have to consider the psychological factors. Trusting robots is not easy and can be a stressful task, especially if you're not understanding how the robot itself works. So in order to have mission cohesiveness, team dynamics need to be considered when incorporating a HRI into your missions. Then we also have the issue of technological limitations. Many of the robotic systems that we used to use are now outdated because of their legacy programs that they depend on. So as technology grows, we have to keep up to date with it. Otherwise, we will fall behind and the robots that we use will no longer be useful for more complicated missions in the future. And finally, we need to have some sort of system cohesion when it comes to technology. System cohesion just means that every part of the robot should be in cohesiveness with each other and making sure that every part is not built by a different person in order to make sure there's no inconsistencies in the system itself. And when we talk about the ethical and safety concerns, safety is of the utmost priority. NASA must ensure that the robotic systems are highly reliable because any failure could pose serious threats, such as causing damage to the equipment, such as the International Space Station, or even endangering lives. And when we talk about task allocation, we must make sure that the robots complement the human capabilities without undermining the human experience or trying to take over too many tasks that could detriment the mission. So now the paper discusses the different methods in which HRI is possible in space. There's two kinds that we first see, which is direct versus supervisory control. Direct is when we have teleoperation and direct manual control over these robots, as seen in the SSRMS on the International Space Station. Whereas a supervisory control, as we mentioned, happens to be high-level commands that the robot can execute autonomously. The next communication that NASA is actually leaning more towards, now that we're going towards more autonomous systems, is trying to incorporate multimodal cues to improve interaction. This means gesture recognition, verbal commands, and visual monitoring systems. So humans often communicate non-verbally, and this can be very difficult to replicate with robots. And when you're in a human-robot environment, when many split-second decisions can be taken based on these social cues, it is important that the robot is able to recognize them. So this kind of intuitive communication between humans and robots is one kind of communication method that NASA is working on. We also see an open loop operation method of communication, meaning that direct commands are sent, executed, and feedback is provided. This loop helps the engineers understand where, if any flaws are there, and if they have any chance for oversight, which can be eradicated. The final thing is collocated versus non-collocated method for interaction in space. Collocated methods is the interaction where humans and robots are in the same physical location. This means they can have real-time feedback with more intuitive communication and immediate problem solving. So they're both present in the same space. Whereas in non-collocated, we only have remote control with communication delays and where the operators are separated from the robots. So they're either separated by a huge distance or a huge time gap between when they receive the commands and when they actually execute them. So this kind of method is especially useful for hazardous environments where we want to necessitate robot autonomy and utilize our robust communication systems so that we don't endanger the lives of astronauts. Now we discuss the results and achievements in NASA's HRI efforts so far. First, we see that the Mars exploration rovers and the laboratory have been a huge success. So the Mars Science Laboratory has conducted many successful exploration missions using these rovers, demonstrating the robot's ability to function autonomously in extreme environments. So they are already overcoming one of the challenges they have faced in the past with robots in space. The other thing we see is teleoperation results with the K-10 rover and the Canadarm being used on the International Space Station itself. This demonstrates the feasibility of surface telerobotics, where astronauts in orbit can control robots on the planetary surfaces. So that opens up the door for more advanced repairs to take place in the future, especially when the humans themselves can't exit the vehicle to make those repairs themselves. Then we see the free-flying robots in space, so the Astrobee and the spheres. They are successfully have been integrated into astronauts' lives, with maintenance and monitoring duties being taken care by them. So in this way, they are paving the way for future intravehicular robotic systems. So intravehicular robotic systems just means that within the International Space Station itself, we have many more mini robots that are able to transport things back and forth or move around and have that dexterity. And then finally, we see that they have achieved great progress in the ongoing autonomy and lunar exploration developments. And this is something that we'll discuss in the upcoming slides a bit more, but they have made real-time improvements for navigation, decision-making, and even resource utilization. So with the tests that have been conducted so far, we can make more projects that are ambitious due to the achievements of these current experiments. As discussed, we will now talk about the future HRI opportunities in lunar and Martian missions. First, we talk about the Gateway Lunar Outpost. The Gateway Lunar Outpost is a small outpost orbiting the Moon that provides vital support for a sustainable living for the astronauts that will land on the Moon. So, for the large part of the year, this gateway will be unoccupied, meaning that it will rely heavily on robotic systems for maintenance and operations while astronauts are absent. So the HRI tasks that will be involved will be the intravehicular robots that perform the routine maintenance, monitoring, and diagnostics for the gateway. The robots will be tasked with managing life support systems as well, and monitoring environmental conditions and performing basic repairs. So on the topic of intravehicular robots, in the future we will see more collaboration with these vehicles, especially for real-time assistance such as system inspection and surface sampling. Especially since we've discussed about the harsh conditions, if a human cannot go out and sample the environment themselves, these vehicles can take their place and crawl around the inside of the vehicle or outside and rearrange cargo, collect samples, inspect some issues, and even perform maintenance. And the next advancement that we can see is in the lunar rovers. So future lunar rovers will be able to extend the surface exploration distance, enabling astronauts to cover larger areas. So they will be able to travel faster, they will be able to travel further, and they will have access to new features that are not available right now, such as terrain navigation, mapping, and resource collection better than ever before. And the new feature that I would like to highlight is the transition between human command and autonomous operation. So in times of distress, where the human is not able to react fast enough or does not have access to the control panel of the lunar rover itself, the lunar rover should be able to take autonomous control and carry out with the safety procedures or get through the emergency. Next, we have future plans for the Artemis mission. The Artemis mission is about robots constructing lunar habitats and processing in situ resources, meaning the robots themselves can construct houses or laboratories for the astronauts to land in, and on top of that, they will also be able to provide oxygen and food from the lunar soil themselves. So the HRI tasks here will involve monitoring not only the habitats but also the astronauts themselves while building these structures and after the structures have been built. And they will also prioritize effective communication methods between ground control and robots for large-scale construction and resource extraction. So with the help of the lunar rovers and the Artemis mission rovers, we should be able to travel large distances, gather the resources required to build these habitats, and bring them back to the base camp, where the Artemis mission robots will be able to construct these habitats from scratch with the materials available on the Moon, and then take care of the astronauts that are going to be residing in them. About the future plans for HRI in Mars exploration and the rovers that they will use there. So we have many next-gen Mars missions lined up. The first being the Phoenix Mars lander and future Mars missions that will aim to improve systems by integrating more autonomy and reducing operational latency. So as I mentioned before, to get commands to Mars, it takes between 6 to 44 minutes in order for the robot to receive the commands from the ground control station on Earth. Hence, we will be aiming for more autonomous control to reduce this latency. So the HRI task that this Phoenix Mars lander will be able to do is to help ground operators remotely instruct and monitor robots with limited communication windows and take care of running missions efficiently without contact to Earth. Then we have the surface exploration robots. The Mars rovers will feature enhanced capabilities such as improved navigation and once again in situ resource utilization. So they will be able to also perform soil analysis, navigation, and excavation tasks. So operators can manage the rover remotely, or they can give them high-level program commands that the robot can execute autonomously. And then we talk about human-robot teaming on Mars, the most important topic in my opinion, because it will play the most key role in constructing habitats, collecting samples, and assembling structures. So HRI will allow for the remote oversight of robotic tasks such as habitat assembly and resource extraction. So for the first couple years until these environments are set up, it may not be safe to send astronauts to Mars directly before having organized a place for them to stay. So hence we'll be sending these robots first such that they can assemble the habitat and mine water for these humans to have as resources once they land, along with oxygen supply as well. So they will collaborate in real time, performing critical tasks autonomously when direct input is limited due to communication delays. So even if no one instructs the robot from Earth for a couple days, the robot should still be able to continue its tasks autonomously. So, to conclude the paper, human-robot interaction is essential for efficient and safe space missions on Moon, Mars, and beyond. So, especially in space, where everything can be very complex, with the multitude of challenges that we've seen with the communication delays, issues related to safety, related to the environment, the continued innovation is crucial. And this continued innovation will take place in the form of advanced teamwork and advanced autonomy systems within these robots that will allow for seamless HRI both on-site and off-site with remote collaboration. And the future vision, as we've seen with Gateway, as we've seen with Artemis, as we've seen with the Mars missions, NASA is shaping the future of HRI, enabling human-robot systems to work across vast distances, even when communication is a problem and even when the environments are against them. Thank you so much.